This is my favourite photo, even though it's only half finished here, because it conveys what I was going for in the sense of aesthetics, in that it was supposed to be confusing about exactly what era it was made in. Hello and welcome to what is undoubtedly my highest quality video if we discount anything that is entirely computer generated. It's probably also the most intense and quite possibly also the least coherent. This is part one of a two-part video. It's made from old and new footage. Some of the old footage hasn't been shown before. This part is about how to spend a whole year putting together an electronics project. In a short video, I'm probably not going to be able to keep up myself. Let's start with a rubidium frequency standard that are commonly available from eBay. It's not one of the fixed frequency ones, this one's programmable, and I assume this is a 10 MHz sine wave. These units used to go real cheap, but they became more expensive as they became more popular. You can see here I've started to put together a copper frame. It all gets painted later on. This should all go roughly in chronological order, but there'll be a few slip-ups. To get my 10 MHz frequency from my frequency standard to an LM7171 frequency amplifier, I've used this semi-rigid coax assembly. Here's the frequency amplifier PCB. You can use these to make a small distribution amplifier, but I'm just using it to clock a microcontroller, and this is a brass shield that I'm using to cage it. It sits on the corner of a RealTime Clock PCB, which also contains a controller for speech and a small audio amplifier. And we've of course returned to recent footage of the clock board, and it will also show the rigid coax assembly leading through cable guides to the clock board. Now that the microcontroller is clocked with a stable clock, we can generate another frequency with the microcontroller, and here's a gate timer made of a bunch of frequency dividers, which is used for a frequency counter. Now it's possible to tap a signal at any frequency divider on the gate timer board to get a number of different frequencies. Here's a second LM7171 high frequency amplifier for receiving an external frequency to measure with the frequency counter. Now to actually count the frequency, I used a bunch of decade counters and bar graph displays. This picture was actually called 50 wires to go because I set myself the task of wiring 10 wires every night for one decade counter to get it done in a week, roughly. That was after work, a working week, and I didn't get home till late, so it wasn't easy. Take a look at it. Those two boards are fairly simple on paper, but a bit of a monster in reality when you're prototyping. These are a couple of cable guides to lead some non-rigid coax around, and a small daughter board for the reset timer circuit. Since the microcontroller is producing the master frequency for the frequency counter, it knows when to do the reset. A flip-flop on the gate timer board alternates the enable pins on the decade counters to provide a time when you can read the displays and a time when it's counting. For demonstration, the frequency counter is counting the same 10 MHz signal as the microcontroller receives for its input. A microcontroller could manage all of this in software, so for no reason at all, it's mostly happening the old-fashioned way. The real-time clock will need some type of display, and these are blue 7-segment displays. They're just covered in white tape to protect them while I'm soldering. Here's some kind of preview setup that I don't even remember doing, followed by a test power-up. So this is the frequency counter, power supply, gate timer, real-time clock board, and the display, which is multiplexed. The aluminium chassis pan shown here is the only part I didn't fabricate myself. It's also the part that introduced the most error into the dimensions. You can see the power supply on the right there, which is a bunch of 7805 regulators, and this is the aluminium platform and standoffs to support that. Then the first rigid cable guide to get power from the main power cable at the back through to the power supply, through the junction in the middle, and to the port of the rubidium frequency standard at the front. This one's just for speaker wires to lead audio from the clock board at the back to the speaker at the front. The 8-digit display is multiplexed with a decade counter if I remember correctly, and my memory's not that great. It's been a long time since I've worked on this. I didn't remember at all that the day of the week is displayed using the decimal points on the 7-segment displays. The RealTime Clock chip has got its own calendar. And the rolling odometer effect on 7-segment displays. There's a DTMF code that controls the speed of that rolling or whether or not it happens at all. And that roughly brings us to the picture at the start of this video, about halfway through the project. The rubidium frequency standard runs quite hot, about 50 to 70 degrees depending on the outside temperature, and this heat sinking mass is next up. Time Splitter. It's not just a name I made up to rehash an old project and make a new video, and this proves it. Quite a lot of mucking around on this before I finally made up my mind. The idea here was to sand back the solder and paint over all of this and just have a texture that I could read the text through, but I scrapped that, and there's some acrylic paint, and then I think this one's a different color again just by applying another coat. But then I gave up on that completely, sanded the whole thing back, peeled the label off, sanded back all the solder and started with a clean slate because I liked it better. Now, a clock that's going to talk to you needs a speaker. Yeah, the amplifier has a volume control. Perhaps I should have turned that up. The speaker I mucked around with a little bit too. This coat of paint here, I didn't leave that way. I roughed it up a bit. I was looking for something a bit older, I suppose. Not sure if I even prefer it, but I'm not mucking around with it again. If a clock talks, it might as well swear at you when you enter an invalid input for a time. The clock is only casually set with DTMF. It would normally set itself using the GPS, and that's covered in the next part. DTMF commands are used for some other functionality though, such as what I mentioned before, changing the speed of the rolling odometer, changing the gate time for the frequency counter, and a few other things. This board under the clock board has the DTMF decoder and the microphone preamp, as well as a serial transceiver. I've previously done another whole video on the astronomy board. It receives serial from the GPS, controls the LCD, and talks to the clock board. Some of the parts I haven't covered will be covered in the next video. Primarily, it tells the clock board the time that it receives serially, and then also tells the clock board when to sync on the pulse per second signal that the clock board is receiving from the GPS unit directly. My heart sank when I found this photo. She's there because I'm there, and that's Spanky all over. One of the LEDs on the astronomy board indicates that the sun is currently up, and another one indicates that the moon is currently visible in your position. The LCD display wants a fancy shroud. There's a bit of a story behind this. I was given some old kit by a member of our ham radio club that was previously donated by the family of an amateur operator who's no longer with us. This material was part of an enclosure for one of his old projects, and I think it's kind of cool that it becomes an enclosure for another project. Greetings to the current and the former VK4QT. I admire your dad's work, and some of it was saved for the long term. This is a bit of planning for the software LCD transition effects. And following that, the same for the core memory read and write visualizations. You'll see them in the next video, and there's also another video with a short segment on it. The one coming up is the spin. And then we have some planning for the rolling odometer text transition. This one's one of the first examples. I don't think I've ever played it anywhere before, and it runs fairly slowly, so this one's sped up 2 by, and it's still much slower than I ended up implementing it. It does show you though that there's only ever 8 characters moving at a time, and they're your 8 custom dynamic characters. This one's called diagonal swipe. The code for this is all released on SourceForge. That's the text transitions. There's 4 or 5 of them, I think, and I think the way I implement it here is I cycled them. So it'll only be the diagonal one, and then the next round will be something else. Basic digital compass. There is another video of a short segment of how this works, and it will also be shown in part 2 of this video. Yeah, bit more shabby than the LCD shroud, but it'll do. There's a few paint planning sort of previews that I've done here, and it was just masking with a paint program just to see what would work best, and I don't think I ended up following any of them. Maybe that one's the closest, and the way it ended up was like this. This was my first go at a QFH antenna for GPS, and look, it's got cobwebs on it now. It didn't when I made it though. This was also my first go at prototyping a part so small. I'm much more confident with that now, but I was pretty scared this time, and I was also excited when it worked. This is an optional EEPROM it can use to store almanac data, but I didn't end up using it, so it's still sitting in a drawer somewhere. No EEPROM or battery backup, which does mean that the GPS has to start cold each time. Here's a bracket made of standoffs to fix the GPS unit to the rest of the device. It's copper plated, and even the screw heads are copper plated. And installed on the rest of the unit, and you can also see yet another cable guide. This is the power and serial cable for the GPS. As mentioned before, the frequency pulse per second output from the GPS is directly connected to the clock board so that it can sync when it's told to. Core rope ROM. Now this one's quite extensively covered in previous videos, so I won't spend a lot of time on it. It was intended for this project. It stored the locations of every capital city in Australia. At least it did until I smashed it. I never really did have a place to put it anyway. This one did have a little problem. I wouldn't call it a failure, but it had to be run outside of specification to get it to work properly, basically at a higher voltage. Yeah, if I made another one, it would be spot on. Beautiful, isn't it? There's some planning for you. If you look closely at that coloured heat shrink, that forms a pattern. It groups wires into the floats that form the geolocations for the capital cities. No joke. And finally, core memory. This is what the project's all about, really, not atomic clock stuff. It's my favourite project of my life by far. Followed close behind by something as simple as a crystal radio I put together when I was about 10 that I got a lot of joy out of. This core memory project in itself is also extensively covered in previous videos. There was no mention though of how it integrated with this larger project, and that will come into play in the next part of this video as well. The standout memory for this project all up is that I had to do a huge amount of work before I had any idea that it worked at all. Fortunately, though it does work very reliably, there's been a timed 3-month period where I've stored a geolocation on it and read it back successfully. Then after that, there's been a period much longer than 3 months where I've done the same. A 64-bit core memory module, capable of storing 1 geolocation. These are some current drive resistors, or current limiting resistors, to provide a little more than half of the coercive current required to flip 1 core. It's just as well I write stuff down and name photos, because I don't remember all of this. The rectangular BH curve, otherwise known as a square loop or a hysteresis curve. A mandatory graphic for any modern core memory project, or you'll be mocked and ridiculed, and I'll lead the brigade. I wish it was as clean looking as that now. Actually, I don't mind patina, I just like uniform even patina, and I've left some fingerprints on some of the brass I noticed when making this video, so I'll clean that up and start again. This is the toroid transformer used in the sense amplifier, and unfortunately I remember getting stuck in and then regretting that I didn't take any photos. It's pretty much a sealed unit, unserviceable. I'm proud of that enclosure though. It amplifies very short, low voltage pulses from the sense wire in the core memory module, and everything is shielded on the way to here. This is an LED test board that plugs in place of the core memory module to test the matrix addressing. When this worked, that was the first time I really had any idea that the whole thing would work. For some reason I had an original photo of it half completed and had to get a YouTube screenshot for the completed version. This is the glamour shot that was on Hackaday, and yes, I did have a purpose for it the whole time. I didn't just make it and then find a use for it. Yeah, you know, it was kind of made to sit on this platform in this little nook on this little atomic clock thingy bob. As I said in the last video, it's not exactly sitting where it should be. It's meant to be lower, and there is some mechanical adjustment to make before I can get it there. The whole thing is finished in terms of electronics. Looking at this photo again, you can see a stamp there that says core memory 64-bit, and it looks like I just put this all on the paper and made a stamp for it, but it was really to make little plaques like this. I never actually used it. It's still in a bag, and that's why it's still shiny and it doesn't have any of the patina. I wasn't entirely happy with it, but I wasn't so unhappy that I threw it away. You can see where it was supposed to go, bearing in mind that all sits lower, more like next to the LCD. This is an example of one that I don't have anymore, I was unhappy with, and I did throw away. In this video I'm giving away the complete documentation, and here it is, so pause the video and you can reproduce the project yourself. Yep, that is the documentation. Well, that was more than 18 minutes. If that seemed like closer to 10 minutes for you, then you enjoyed the video and you owe me a like. I didn't really explain operation, and that's where the next video comes in. It's actually what the whole thing's for and what part the core memory plays. So I hope to see you then. Bye.